It's good to be with you once again. Today we are going to talk about cylinders and quadric surfaces. Cylinders and quadric surfaces. We've already looked at two special types of surfaces, planes and spheres. We also looked at lines, but those are not surfaces. Here we're going to investigate two other types of surfaces, cylinders and quadric surfaces. In order to sketch the graph of a surface, it's useful to determine the curves of intersection of the surface with the planes parallel to the coordinate planes. These curves are called traces, or cross-sections of the surface. A cylinder is a surface that consists of all the lines that are parallel to a given line and pass through a given plane curve. Looks like there's a little typo here. Should be here through a given line and pass through a given plane curve. The following are examples of cylinders. In figure 1, we have the parabolic cylinder with equation z equal to x squared. In figure 2, we have x squared plus y squared equals 1, which is a circular cylinder. And in figure 3, we have y squared plus z squared equals 1, also a circular cylinder. Notice the difference between figure 2, figure 3, is that in figure 2, the cylinder is centered on the z-axis. So notice it's centered on the z-axis here, and notice down below, there is no z. In figure 3, notice that we're centered on the x-axis, and down below, there's no x. That might prompt us to look back at figure 1. Notice in figure 1, we're centered or kind of parallel, symmetric. If we take cross sections that are perpendicular to the y-axis, and notice that there is no y. When I say no y, I'm saying there's no y in the equation above. When I say there's no z, I'm saying there's no z in the equation above. When I say no x, I'm saying no x in the equation above. So notice that in each equation, a variable is missing. This is typical of a surface whose rulings are parallel to one of the coordinate axes. If one of the variables is missing from the equation of a surface, then the surface is a cylinder. In this manipulate, we will show how you might sketch a cylinder. So first, we're going to sketch the basic trace in the appropriate plane. So in this case, we have something like x squared plus y squared equals 1. And so I sketch the circle it's given here, and notice that I'm sketching it along on the xy plane. Then we come through and we draw a second trace in a plane parallel to the basic trace. So here's this second trace. Notice that it lives on a plane that's parallel to the xy axis. Parallel, sorry, not xy axis, but xy plane. Parallel to the xy plane. Then we draw parallel lines through the two traces. So a whole bunch of vertical lines kind of connecting one trace to the other. Notice all these lines are parallel and they extend a little bit below the bottom trace and above the top trace. To give definition to this cylinder, now we're going to draw a light outer edge parallel to the traces. So we're going to sort of draw a top and a bottom. So here, kind of this light little top. And we got this light little bottom. And finally, if we put all these things together, we have graphed the elliptic cylinder. There you can see it with the trace along the xy plane, the one above it, the vertical lines, and then a nice little top and bottom. And that's how you graph an elliptic cylinder. In example 1, we want to graph x equal to sine z. We could try this same technique that we just learned about, and then we can look at manipulate where this happens. So let's do it by hand so you get sort of the rough sketch idea first. So I'm going to start by drawing my basic coordinate axes. So z, x, and y. And then I want to graph x equals to sine z along the xz plane. So I'm going to draw it along the plane that includes both x and z. So notice that this is a sine, but it's a sine that's kind of coming, it's working vertically. So here would be pi, 2 pi, and it's entirely along that, or on that xy or xz plane. That's my first trace. Then I'll draw a second trace of the same thing. Okay, so there's my second trace on a plane parallel to the xz plane. So notice this is supposed to live on some plane such as that. And we draw horizontal lines. This is not my best sketch ever. Okay. And now we want to lightly draw those endpoints so we can see what's going on here. Something like that. So there is our sine-shaped cylinder. It's a cylinder because you have that same profile as we work along the y-axis. Here's an animation to show that same curve sketching process. So we start by sketching the basic trace on the appropriate plane. In this case, that appropriate plane would be the xz axis. Notice how that red curve is sitting on the xz plane. Then we draw a second trace in the plane. So again, they're both living on planes parallel to the xz plane. I think I said xz axis, I meant xz plane earlier. And then we will draw parallels across the two traces and lightly sketch that outer edge. It's a little difficult in one note to erase the ends, but with a pencil that wouldn't be very difficult. And this gives us our cylinder. Notice cylinder has the same profile regardless of where you cut it along the y-axis, provided your cut is parallel to the xz plane. So that's how you sketch a cylinder. Quadric surfaces are the counterpoints in 3 dimensions of the conic sections in the plane, the parabola, the ellipse, and the hyperbola. And so we have the ellipsoid, which has equation x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. All traces are ellipses. If a equals b equals c, then the ellipsoid is a sphere. We have the elliptic paraboloid, which has an equation such as z over c equals x squared over a squared plus y squared over b squared. Here, the horizontal traces are ellipses, the vertical traces are parabolas. The variable raised to the first power indicates the axis of the parabola. We have the hyperbolic paraboloid, which has the form z over c equals x squared over a squared minus y squared over b squared. Notice the difference between the two. Here's a plus, here's a minus. Horizontal traces are hyperbolas, vertical traces are parabolas. The case where c is less than 0 is illustrated. So these are also called saddles. At this point right here, is called a saddle. We have the cone, which has the equation z squared over c squared equals x squared over a squared plus y squared over b squared. We have, in this case, horizontal traces are ellipses. Vertical traces in the planes x equals k and y equals k are hyperbolas if k is not 0, but they are pairs of lines if k is equal to 0. Finally, we have the hyperboloid of one sheet, which has the form x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Here, the horizontal traces are ellipses. Vertical traces are hyperbolas. The axis of symmetry corresponds to the variable whose coefficient is negative. And we also have the hyperboloid of two sheets, which has the form negative x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. Here, horizontal traces in z equals k are ellipses if k is greater than c or c is less than negative c. Vertical traces are hyperbolas. The two minus signs indicate two sheets. So here, the two minus signs, 1, 2, indicate two sheets, 1, 2 sheets. And up above, you just have one minus sign, and so it's a hyperboloid of just the one sheet. Let's look at some animations to help us understand each of these 6 shapes. So this is an ellipsoid. What I want to point out is that the traces are going to be ellipses in all directions. So the traces are ellipses as we move along the x-axis. Remember, the trace is this line where the surface is intersected by a plane parallel to one of the coordinate planes. So our traces are ellipses in that direction. Our traces are also ellipses if we move along the y-axis, and our traces are ellipses if we move along the z-axis. So this is the ellipsoid. Here we have the elliptic paraboloid, or the paraboloid. Okay. And what I want to point out is that our traces along, as we move parallel, we're moving along the x-axis, but notice that all of these traces are all parabolas. If we look at traces in the plane y equal to y naught, traces as we move along the y-axis, again, they are parabolas. And if we look at traces as we move along the z-axis, our traces are all ellipses. So this is the elliptic paraboloid. Here we have the hyperbolic paraboloid. Notice that saddle point. Think about like the saddle on a horse. There's our saddle point. Notice that we have traces that are that look like parabolas going downward one direction. The traces look like parabolas facing upward, going the other direction. And if we cut this parallel to the xy plane, notice that we have hyperbolas, except for at the point right where z equals 0. And right at that point, it looks like there's a little x showing up for our trace. So again, the horizontal traces are hyperbolas, the vertical traces are parabolas, and this whole shape is the hyperbolic paraboloid and gives us a nice saddle picture. Here we have a cone, or an elliptic cone. At first glance, this might not look like a cone, but notice if we rotate it, it's got some cone-like properties. Okay. The equation is given below. We look at the traces when x is equal to x naught. Notice that we have ellipses. And as we move along the x-axis, notice it's in our equation, we have y squared over 4 plus z squared equals 4x squared. So here we're moving along the x-axis there. So it's almost like we're fixing a radius, if you will, of a little ellipse. It's not really called a radius on ellipse, but you get the idea. We look at traces parallel to the y-axis. Notice that we have hyperbolas. And if we run parallel, well, in the plane z equals z naught, again, we will have those hyperbolas. So horizontal traces are ellipses, vertical traces in the plane are hyperbolas, assuming the variables are as they are set in the book. So this is a hyperboloid of one sheet. Sort of looks like a cooling tower at a nuclear power plant, if you're familiar with what those look like. So if we look at traces in the plane x equals x naught, notice you have those hyperboloids or hyperbolas. We look at traces in the plane y equals y naught. Again, you have the hyperbolas. And if we look at traces in the plane z equals z naught, or parallel to the xy plane, you'll get nice ellipses or circles, depending upon the case. So this is a hyperboloid of one sheet. It's one sheet because it's one continuous thing. There's not a gap in the middle, if you will. That's the hyperboloid of one sheet. And finally, we have the hyperboloid of two sheets because there's two little sections. It almost looks like two elliptic paraboloids, one on top of the other, but these aren't paraboloids. These are parts of a hyperboloid of two sheets. So if we look at the traces in the plane x equals x naught, you'll see those hyperboloids, hyperbolas showing up. We cut it the other direction. Again, you'll see the hyperbolas showing up. Remember, hyperbola is sort of like it's almost like you have a parabola aiming one direction and then another parabola aiming the opposite direction, kind of across from it. They're not actually parabolas, but they sort of remind us of that shape. And finally, we have the trace in the plane z equals z naught. And what's important to note here with the hyperboloid of two sheets is that you have the ellipses above, you have the ellipses below, but there's sort of a gap in the middle. And it's that gap that gives it the two sheets. So there you have it, the hyperbola of two sheets. In example 2, we want to identify each quadric surface and graph the cone and elliptic paraboloid if there is any. So what we're going to start with is kind of try to identify which world we live in. And so specifically, I want to look at the powers. So notice square, 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 square. And notice that you have in B and E, you have no squares. And so since there's no squares in those examples, they must be either the elliptic paraboloid or the hyperbolic paraboloid. So really what we care about are the signs. So in B and E, what we care about are the signs. So this in B, sort of using process of elimination, we are of the form z over c equals x squared over a squared plus y squared over b squared. So what I'm focusing in on is that plus. So this tells me that what we have is an elliptic paraboloid. by process of elimination, we might expect that E will be the opposite, but just to double check, we're of the form Z over C equals x squared over a squared minus y squared over b squared. And again, what I'm focusing in on here is the minus sign, and that tells me that I have a hyperbolic paraboloid. Hyperbolic paraboloid. All right. If I look back at A and B, what I want to point out is the number of negatives. So notice there's one negative in A and two negatives in B. And in the first case, we're equal to 1. In the second case, we're equal to 0. So if I'm looking for A, and I was looking for one negative and equal to 1, I would notice, oh, gee, this is of the same form as the hyperboloid of one sheet, x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Now, it's a hyperboloid of one sheet. It's not going to be along the same axis. Like the form that's given on the handout would be a vertical hyperboloid of one sheet. And now in what we're given in A, we've got a horizontal hyperboloid of one sheet that's going along the y-axis instead of kind of up and down along the z-axis. But either way, it will work. So the hyperboloid of one sheet. And then in D, I notice that we're equal to 0. So we have all those squares and we're equal to 0. So that means the origin must be included in this particular equation. So we're of the form z squared over c squared equals x squared over a squared plus y squared over b squared. Notice that in the equation that's given, everything is moved to one side, which is why you have equals 0. But this would be the equation of a cone. And if we fast forward our way to C and D, again, we notice all those squares and just the one, here's a first power on the Z. And so in C, we notice all those squares equal to 1, and we've got two negatives. So this must be our hyperboloid of two sheets. That's of the form negative x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. Our hyperboloid, two sheets. We could figure out what f is by process of elimination, but again, trying to stay away from that. We notice that there's two squares, one lower power, and if we, you can think about this z minus 5 as being a shift vertically by 5. And so all this stuff would be equal to 0. So I want an equals 0 with only one with an equals 0, or I want a z equals x squared plus y squared. So this, in this case, we would be of the form z over c equals x squared over a squared plus y squared over b squared. And this is an elliptic paraboloid. So there is our, we have one more to look at. So I have, in G, I have x squared plus y over 4 squared plus z squared equals 1. So this is of the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And this would be an ellipsoid. So all that remains is trying to sketch these various critters. So let's see if we can sketch them one at a time. So in A, we want to graph a hyperboloid of one sheet, and specifically, we want a hyperboloid of one sheet that is along the y-axis. Along the y-axis. The reason we want it along the y-axis is because right here, we have this negative y squared over 25. And so we wanted to graph that. We would know that it's along the y-axis. Okay. And then we can add our axes in place. Here's our y, our z, and our x. And we could see that our x's are going to come out at 5 because we have x squared over 25. And our z's are going to come out at 7 because we have the z squared over 49. So there is our hyperboloid of one sheet. In B, we have an elliptic paraboloid, and our elliptic paraboloid has just that z with a single variable. So here we will be along the z-axis. Again, the reason it's going to be along the z-axis is because the z just has a power 1. That's kind of the variable that's showing up for us. And so we can draw our elliptic paraboloid. Something like that. Add our z-axis. And we notice that this thing is going to go through the origin. So it'd be true when x equals 0, y equals 0, and z equals 0. So we know it goes right through the origin. Okay. And I'm not really worrying about which particular dimension is bigger, if it's wider or taller. I'm just trying to get that general shape. In C, we're looking at a hyperboloid of 2 sheets, and this is going to go along the x-axis. It's along the x-axis. The reason it's going to go along the x-axis is because we have only one of these variables being positive, kind of the one that stands out. It's the plus x squared, so we're going to go along the x-axis. So I can draw a hyperboloid of 2 sheets away, so I know it's going to go kind of point in and out. Something like that. And then we need to get our axes in place. Something like that. And we know there's y, x, and z. And we could ask ourselves, where does the hyperboloid separate, if you will. And so to do that, we could say what happens when y and z are both 0. So when y and z are both 0, so y equals z equals 0, you're just left with x squared equals 1, which would tell you that the two endpoints of the two sheets would be at x equals +1 and x equals -1. So there's your hyperboloid of two sheets. Continuing with the pattern that we've had previously, we're going to try to graph the cone, and we notice that one of the variables, the z, has kind of a different type of pattern in the signs. And so by this point, you probably guessed that this will be along the z-axis, and it's a cone. So cones are kind of easy to draw. So you kind of draw an X and do a circle on the top and bottom of the circle below. Add your axes and away you go. In E, we need to graph the hyperbolic paraboloid. This is kind of the graph that requires perhaps the most thinking of all of them. And so again, notice the z equals 1. So 1 power. So specifically, this is going to be a kind of an upright shaped saddle. So it's going to be a saddle you could sit in. You can sit in versus one that's on its side, if you will, which would happen if it was x equals or y equals instead of z equals. So let's graph that hyperbolic paraboloid. And here I'm going to mess around with my axes a little bit just for the sake of graphing. And so if I have a smiley parabola, I can start by graphing, and then I graph with two little sideways bits. That's kind of the top of my saddle. And I'll graph the downward bit of the saddle with sort of a forward shaping parabola. Down, down, down. And then your downward facing parabola continues backwards into the picture and connects up on the other side, continues backward here. So there's your saddle. One thing to note about this particular saddle and the way I've drawn it, in order to make the picture look nice, because honestly, this is the direction I can draw saddles in the best, I've actually drawn it so that the x-axis is going right to left, the y-axis is going forward, and the z-axis is going up. That's because saddles are a little bit of a nuisance to draw, and this is the way that I'm the most comfortable drawing it. Maybe some of you are better and you can figure out how to show me how to draw the saddle oriented more towards us, but that's out of my skill set. In F, once again, we're drawing an elliptic paraboloid, and so this is going to be vertical. Again, because that the z is on its own. But here, instead of orienting it centered at the origin, I'm going to try to center it at the point 3, -2, and 5. And so rather than overthinking, what I will do is I will simply draw my paraboloid and then create my axes around it. So here's my upward facing smiley paraboloid. Something like that. And now I got to ask, where is this? So I know it's going to be upwards. And so this point that it's over is the point 3, -2. So I'm 3 in the x and minus 2 in the y. 3 in the x, 1, 2, 3, and then 1, 2 in the z. And so my vertical axis is here. There's my z-axis, x and my y. Okay. And I know that the height where I'm hitting is going to be at 5. So this right here would be the point 3, -2, 0. And the tip, the bottom of it would be at 3, -2, 5. So there's my elliptic paraboloid, but centered at another point. In G, I want an ellipsoid. Think a sphere, just kind of like squashed one way or the other. So we can draw some sort of an egg shape, if you will, or a sphere shape. Something like that. Add our axes to the middle of it. So y, just back to the traditional axes, x and z. And if you think about what happens when y equals 0, I've got a circle going through 1 and 1. When z equals 0, I've got an ellipse. And I think I got to go through plus or minus 2 in the y. And when that was when z equals 0. When x equals 0, I've got an ellipse. And again, my y is going through 2. So it's kind of an egg shape. It's a little bit longer in the y direction than in other directions. So as we wrap up this section, I just wanted to comment that math is crazy. So 2 spheres can be formed from 1. Yeah, that's right. So if you can look it up, the Banach-Tarski paradox states that given a solid ball in 3-dimensional space, so not just a surface, but a solid, there exists a decomposition of the ball into a finite number of disjoint sets, which can then be put back together in a different way to yield 2 identical copies of the original ball. Indeed, the reassembly process involves only moving the pieces around and rotating them without changing their shape. And so we can take 2 balls or 1 ball and turn it into 2. Well, and then you should be able to take 2 and turn it into 4, et cetera, et cetera. So somehow there's this weird thing going on. That's certainly well beyond the scope of this class, but it's just a reminder that even things as simple as spheres and quadric surfaces can have some exciting things if you continue to dive into this beautiful topic of mathematics. So there's everything you need to know for today about cylinders and quadric surfaces.